last part of the chapter 12, we're going to talk about sound. The book goes into even more depth. We won't do the last couple of sections that pertain in particular to musical instruments. But we do want to talk about it. It's really amazing. The human ear works by detecting very small changes in pressure on the eardrum. You can picture that mechanical wave, which is a pressure wave traveling through the air. The molecules are oscillating back and forth. When that little pulse reaches your eardrum, it causes the pressure to be slightly higher or lower than normal. Normal atmospheric pressure, sometimes just measured as 1 atmosphere, but in the SI units, it's 1.013 times 10 to the 5th pascals. A pascal is a measure of newtons per meter squared. That's your pressure. That's a really big number. If we were to write that all out, that would be 101,300 pascals. An extremely loud sound, extremely loud, might vary that by plus or minus 30 pascals. A really small sound might only vary that by plus or minus 30 times 10 or 3 times 10 to the, did I write that down? -5 pascals. You can hear that small variation. This represents about 1 part out of 3,000. This represents about 1 part out of 3 billion. So our ears are just incredibly sensitive. They are designed to detect frequencies from 20 hertz up to 20,000 hertz. Now, sounds in this high frequency, those are not comfortable sounds. And truthfully, as most people age, there's a natural loss of hearing at the upper frequencies. So this might be the hearing more of a very healthy 6-year-old. Even by your teenage years, you probably don't hear all the way up to 20,000 hertz. One of the things I always mention is because the ears are such sensitive organs, they're also easy to damage. And once damaged, it cannot be repaired. Inside the inner ear are these little teeny tiny cilia. They're like little teeny hairs that vibrate the fluid in the inner ear. That's what creates the wave that's detected by the auditory nerve. Really loud music, you know what I'm talking about, plugging in those earphones, cranking it way up, can shake those violently and those little hairs break off. They do not grow back. So really makes sense to protect your hearing when you're young because you cannot fix it. Anything that has a frequency that is less than 20 hertz, that's called ultrasonic. Infrasonic. Infra is below. You can still have a sound wave that human beings don't hear. Some animals do. Elephants can hear sounds way down there like 6 hertz, 8 hertz. Probably some big whales maybe can hear some really low sounds. Any frequencies that are greater than 20,000 are called ultrasonic. You've probably all seen the dog whistles that people can't hear but the dogs can hear. That's because dogs can hear higher frequencies up in that ultrasonic range. Bats, there's lots of different animals that have slightly different ranges of what they can hear. People we're pretty much in that 20 to 20,000 range. I doubt I'd ask you any of this on the test, but I want you to be aware. Now, how do we measure sound? One method we use is what we call intensity. The intensity is basically the average power transmitted. Now remember what power is. Power can be either work or energy. In this case, it would be energy. It's energy per unit time. So how much energy per unit time is being transmitted per unit area? So it's power per unit area, or you could think of it as energy per unit time per unit area. If we want to think of a sound source, most sound sources emit sound in all directions. So you can think of an imaginary sphere around it. Here's an imaginary sphere. And the intensity would be defined as the power divided by the area. So if you're out here at some distance r, the area of that sphere, for a sphere, the area is 4 pi r squared. So intensity becomes power over 4 pi r squared. As you move farther away, if we were to draw a larger circle, larger sphere, that sound is distributed over that, you can see the intensity would decrease. In fact, it decreases as 1 over r squared. So we have another inverse square relationship. If we double our distance, the intensity of that sound will drop to 1/4. If we're 5 times away, the intensity of that sound will only be 1/25. We already know just from listening that as we get farther from the source of a sound, that intensity decreases, that volume, we don't hear it because it becomes fainter and fainter. If we want to think about this with two different radiuses, this inner radius R1 and this larger radius we could call R2, if these have the same power source, if we solve for power, it's I times 4 pi r squared. So if we're looking at the first intensity in the first radius, that same power would work for the second intensity and the second radius. We see the 4 pi's are really unimportant. We get this relationship that I1 R1 squared equals I2 R2 squared. Sometimes this is helpful to solve problems. It helps us understand how changing the radius changes intensity. Or you can even write it like this. Again, remember, the intensity goes as the inverse square. It's an inversely proportional relationship. This one's probably my favorite, it seems. You can easily see increasing R1 means that I1 would be less. You can play around with that. Let's look at an example. This one's out of the textbook. I did not write down the number, but it deals with a sound system. And it says the sound system produces 1.0 watts per meter squared. 1.0 watts per meter squared. That's units of intensity. They're telling you how intense that is over a hemisphere of radius 20 meters. You might think of that being something like an auditorium where you can picture a rounded roof. Maybe you're only interested in it over that region. The question wants to know how much acoustic power is required. How much acoustic power do these speakers that are producing this sound need to have? Well, intensity is power over area, so the power would be the intensity times the area. Well, our intensity is 1 watt per meter. A hemisphere has half the surface area of a sphere. It's only 2 pi r squared. Radius is 20. Remember, this was watts per meter squared, so this will definitely come out in watts. Comes out to be about 2,500 watts, or 2.5 kilowatts. So pretty straightforward, as long as you know how to find the formula for the area of a hemisphere. So that's intensity. But truthfully, intensity is not the most common way of describing how loud a sound is. Most of the time we use something called a sound level. Sometimes it's called an intensity level, but I like sound level better. And sound level is measured with a new unit called a decibel. The formula for decibels, or sound level, let's write the word sound level first. Now, let's say sometimes it's called an intensity level, but it's not actually the intensity. It has different units entirely. It's given by this formula. 10 decibels times log I over I0. So first of all of a sudden your Algebra 2 teacher is right, you do use logarithms. If you'll remember, logarithms are exponents, and this is a base 10 log, so our base 10, it's an exponent for 10. I0 is 10 to the negative 12 watts per meter squared. That is the faintest sound a human can hear. Somebody did a bunch of experimental testing and found that people with really good hearing could hear a sound with that low of intensity. You know, you hear the phrase, a pin drop. Maybe you could hear a pin drop. Maybe you can hear what it sounds like. Well, I can hear it. When I brush my shirt, it barely makes noise, but I can hear it. So that's I0. Notice, if I were to put in an intensity of I0, if I is equal to I0, this would become log 1, because the log of 1 says 10 to the what power equals 1, and the answer is 10 to the 0 power. This whole thing would equal 0. So we start our decibel scale with the smallest value we can get is 0 decibels. It corresponds to this intensity, which is the very faintest thing we can possibly hear. Now, if we were to increase that sound, suppose we're talking about an intensity of 10 I0. We have a sound that has 10 times as much energy per unit time per unit area. How many decibels will that be? Well, let's put it in our formula because I just want us to practice. It will be 10 times log. If I have 10 I0 over I0, I don't have to actually fill in my 10 to the negative 12 because they'll cancel. What is log 10? That, again, your calculator, you can press log 10, it'll tell you the answer is 1. But it's nice if you understand, it's saying 10 to the what power equals 10. The answer is 1. this whole thing will come out to be 10 decibels. That's really important. I increased the intensity and I made it 10 times bigger. But the number of decibels only increased from 0 to 10. We went up from 0 to 10, but they're 10 times stronger sound. Let's make it 100 times stronger. I'm going to see how this equation behaves because I may not be that comfortable with logarithmic equations. So if my intensity now is 100 times this I0, it's going to be 10 log, of course, 100 I0 over I0. That's just going to be 100. The log of 100 is 2. Remember, it's always asking, 10 to the what power is 100? That's 2. I'm up to 20 decibels. Okay, think about what happened. I increased by a factor of 10 again, and I only went up 10 decibels. So, at I0, make a little table. At I0, this came out to be 0. At 10 I0, this came out to be 10. At 100 times, this came out to be 20. Let's do it one more time. What happens if we get it up to 1,000 times the intensity? I replace this with 1,000. So here I put in 1,000 I0 over I0. Okay. What's log of 1,000? 10 to the what power is 1,000? Log of 1,000 is 3. 3. This whole thing comes out to be 30 decibels. And I want you to realize what's happening. Every time an increase of 10 decibels actually indicates that a sound is 10 times more intense, has 10 times the energy. So if you have a decibel of 25 decibels and it goes up to 35 decibels, well, that's 100 times, that's 10 times stronger. But if you're at 25 decibels and you go up to 45 decibels, that's 100 times stronger, 100 times more intensity. Okay? There's a table in your book that shows you a lot of values at various things from normal everyday noises all the way up to like really loud rock concerts and what human hearing can tolerate. Let's do a different kind of problem now that we've kind of gotten how that feel for that formula. Every time we increased 10 decibels, the intensity of the sound was 10 times stronger, not plus 10, but 10 times. It says, there's an example. At a distance of 5 meters from the source, the sound level is 40 decibels. So, okay, 40 decibels, R is equal to 5 meters, the sound level is 40 decibels. It says at what distance will the sound level be 20 decibels? Now, there's one very direct mathematical approach, and I'm going to show you that second, where we really crank out the numbers, and some of you will prefer that. But we also can think about it in terms of what we've just learned. If beta decreases by 20 decibels, I is decreased by a factor of 100, or 10 squared. 10 for each, 10 decibels is 10, so 10 squared, or 100. The intensity has to go down by a factor of 100. All right, well, let's think. Intensity is power over 4 pi r squared. If I want to decrease the intensity by a factor of 100, or in other words, I want 1/100th of the intensity, I need to make R 10 times bigger. If I make R 10 times bigger, then I get, here, I'll show you. As you can see, that's 100 times smaller. R needs to be 10 times bigger. Well, what's 10 times bigger than 5? 50. And you go, gosh, I don't know, Miss Hughes, I probably wouldn't have reasoned all that out. And I can totally get not being able to reason all that out. That is actually how the book did it. They said, hey, you need to understand that every time this drops by 10, this drops by a factor of 10. So if this drops by 20, this goes down by 10 squared, or 100. The easiest way to make the intensity go down by 100, or 10 squared, is to make R 10 times longer. Let's do it the other way. The other way is to say, hey, let's just find the intensity. So, if beta equals 40, here's our equation. And I know the value of I0. I0 is always 10 to the negative 12. That's its value. I plug in 40. If I divide by 10 to the negative 12, this becomes 10 to the positive 12 times I. You could also write I over 10 to the negative 12, but I think you all can get that. All right, I just want to solve for I. It may be a while since you've done a log equation. First thing, divide both sides by 10. I get 4 equals log. Tell you what, I'm going to back up. I'm going to change this and put it back in the original form. I over 10 to the negative 12. And now I'm going to say, hey, if I divide by 10 to the negative 12, that's going to be 10 to the 12th times I. What is it? How do you solve a log? To solve a log equation, the thing you want to do is write it exponentially. This becomes, this is a base 10 log. 10 to the 4th equals 10 to the 12th I. If I divide by 10 to the 12th on both sides, I get I equals 10 to the negative 8. I'm going to call that I1. I1, if this is beta 1, this is R1, then I1 is 10 to the negative 8. Still watts per meter squared. All right, let's solve it for 20. I just put a 20 here. When I divide both sides by 10 to get rid of this 10 out in front, I get 2. When I rewrite this in exponential form, I get 10 to the 2nd equals 10 to the 12th I. And this second one, then is going to be 10 to the negative 10 watts per meter squared. That's not surprising. I know that if the sound is down, the intensity is down. In fact, it went from 10 to the negative 8 to 10 to the negative 10. It went down by 100 like I expected. I can use this formula. I1 R1 squared equals I2 R2 squared. If I fill in 10 to the negative 8, 5 squared, 10 to the negative 10, R squared. And I solve that for R. R comes out to be 50 meters. So no surprise, I got exactly what I expected. I think this is probably more easy to understand. You do have to know how to solve a log equation, but you guys have all taken pre-cal, I think. So we should all be good with that. Okay, I think that's all I'm going to work with decibels. Let's go on to now to something called beats. Now, beats is probably the easiest thing in the chapter. So after doing a complicated log equation, it'll be nice to do beats. What are beats? Well, beats are something that actually people who tune musical instruments use a lot. If you have two different waves, they're very similar. They either have the exact same amplitude or almost the same amplitude, but their frequency is off just a little bit. Perhaps you're trying to tune A4 on the piano, which is supposed to be at 440 hertz, and you've got a signal, you've got an artificial tuner or another piano that plays 440 hertz, and you strike the key on this piano. When you do it, you're going to hear something called beats if one of them's out of tune. All right, how does that happen? Well, when you have two different waves that are just a little bit off, say one of them's 440 hertz, and maybe one of them's 443 hertz. They're just not quite right. I don't want to draw them because it's hard to draw the individual waves. I did draw them on my notes and try to show you what happens. But what's going to happen is you're going to get a fluctuation of volume. And it's pretty easy to demonstrate if I had a couple of tuning forks where one was a slightly different frequency. But it looks like this. The wave does this. It gets real big and then real little, and then real big in the middle. And then I'm not doing a very good job of drawing it. But what you hear is you hear wah, 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 wah. If you've ever heard two musical instruments that are just not quite tuned, you hear that, this beat sound where the volume is fluctuating. The frequency for the beats is simply the difference. In this case, 443 minus 440 hertz. In this case, you would hear 3 beats per second. When that piano tuner tunes that piano, if he can have that other pitch going, he'll hear that beat frequency disappear. And then you'll get what you were expecting, which would be a nice even tone with the right frequency. Okay. So beats are really easy. I wish I could demonstrate them. I don't have anything here to demonstrate them with. But if I'm ever back on campus, you can come by and say, Miss Hughes, you said you'd show me beats, and I'd listen. Then maybe I'll do it. All right. The last sound phenomena we want to talk about is the Doppler effect. I'm sure you've heard of it. The Doppler effect is that apparent change in frequency when the listener and the source are in relative motion to one another. You can have a source that's moving toward or away from the listener. You can have a listener that's moving toward or away from the source. Or the source and the listener can both be moving. Now, if they're both moving in the same direction at the same speed, there won't be a Doppler effect because there won't be any relative motion. They have to be getting closer together or farther apart. It helps to just stop and kind of draw a picture. Let's suppose we have some source. Maybe it's a siren, maybe it's a radio, but something's making a sound. It sends out sound waves in all directions. Picture this in 3D if you want. It's like spheres that get bigger and bigger. These are what we call wave fronts. And they're equally spaced. Now, if you have a listener over here, and lots of times I just draw listeners as looking like big old ears. There's my listener. If he stands still, he's going to hear those wave fronts hit him with the true frequency. If it's emitting 300 hertz, then 300 wave fronts will hit his eardrum every second. That's what 300 hertz means, 300 per second. However, if he were to take off and start running towards it, he could actually hear more than 300 a second because it wouldn't take them as long to reach them. If he stands still, he can only hear 300 a second. But if he goes running into them, he literally goes crashing into these wave fronts, he'll hear more. So it's easy to see how if he moves, he'll hear a higher frequency if he moves towards it. The other possibility is he could run away, and it would actually take them longer to reach him, and he would hear a lower frequency. He would hear less than 300 hertz. Or, let's suppose the source of the sound moves. Now let's keep the outer ring because that's where the sound source was initially. But the second sound source, he'd already moved this way. He's moving this way. And so it's going to be centered more like this. You can see it's closer up front, in front of the wave, and farther apart behind the wave. And then by the time he emits this one, it's even smaller. So if your listener's over here, oh, that's a funny ear. Terribly funny looking ears, but okay, ears are funny things. These are bunched up. He's going to hear a higher frequency as this source of sound moves towards him. If he happened to be standing over here, well, these are spaced out. He's going to hear a much lower frequency. So that actually crowds the wave fronts in front of the source, and the wave fronts get spread out behind the source. So over here you hear a high frequency. Over here you hear a low frequency. Now, the book will go into how it derives all of the formulas, but the formula I really want you to understand is this one. It's called the master formula. And it looks like this. The frequency heard by the listener is equal to V plus VL over V plus VS, and I like to do all that, times the frequency of the source. Now we need to know what all of those numbers are. We also need to know that the velocity or the speed of the listener and the speed of the sound can have the possibility of being positive or negative. So we need to be sure we know which direction things are in. This is the speed of sound. And it's always positive. You cannot have a negative. Why? The L is the speed of the listener. And it can be positive or negative depending on how we draw the picture, what's going on. This is the speed of the source. It too can be positive or negative. Now, here's the really important, the positive direction. is always from the listener to the source. Whatever the problem says, after you've drawn the picture, the positive direction might point right or it might point left. Heck, it might point up or down, but we consider the positive direction to always be the direction from the listener towards the source. We need to remember that. That's going to determine what's positive and what's negative. Let's look at problem 52. It's the one that I had picked out here. I'll leave my formula up there. In problem 52, I'm going to kind of read it to you, but you've got a textbook, so you can go find it. It says you're driving at 15.6 meters per second when an ambulance passes you. The siren's frequency is 700 hertz. As the ambulance approaches you from behind, you hear a frequency of 740 hertz. If the speed of sound is 344 meters per second, what's the speed of the ambulance? So we need to draw this picture always. So here's the listener, and it says the listener is going 15.6 meters per second. And coming up from behind is our sound source. In this case, it's an ambulance. They don't tell me how fast, but it's going with some speed. And we know the frequency of its sound is 700 hertz. The speed of sound and air that day is 344 meters per second. It took me a little while to find it, but at the very, very beginning of the problems in this chapter, it says, unless it says otherwise, use 344 meters per second for the speed of sound. Now, most books I know, used to say 343. Doesn't matter. It depends on so many variables. Always in the ballpark of around 340 though. Okay, let's think. What is the positive direction? Well, the positive direction is always from the listener towards the sound, 100% of the time. So in this problem, that's the positive direction from the listener. So if the listener is moving to the right, but positive is towards the left, we have to treat this as a negative 15.6 when we put it in our formula. All right, let's see if we can figure out. It's going to be a little bit of algebra. The frequency the listener hears, they told us that, is 740 hertz. So, fill everything in. The listener hears 740 hertz. We have V. V is 344. That's the speed of the sound, which is always positive, plus the speed of the listener. In this case, the speed of the listener is negative 15.6. Over the speed of sound plus the speed of the source. We do not know the speed of the source. That's what we're going to try to find out. I can tell looking at the picture when I find it better come out to be negative, but I don't put that negative, I just put Vs times the frequency of the source, which is 700. There's the problem. There's the one thing I have to solve for. How you want to fight your way through the algebra is entirely up to you. What I did is I divided by 700 first. That put the 700 here. And this here. I combined 344, so now I have 740 over 700. 344 minus 15.6, it came out to be 328.4. 344 plus VS. I did my very favorite thing next. I cross multiplied. 740 times 344 is 254,560 plus 740 VS. So 740 times all of this equals 700 times all of that. That was 229888. Then I subtracted to get everything over here. 740 VS equals negative 24,680. Then I divided by 740, and I got negative 33.4 meters per second. Then I said, let me make sure that's going to work. First of all, yes, it should be negative. Second of all, yes, they're getting closer together. I know they're getting closer together because the frequency increased. Anytime the listener hears a higher frequency, they're getting closer together. So my ambulance definitely had to be traveling faster than my car. I'm going in my car at 15 points. So they definitely are. So that makes perfect sense. So far, so good. There is a part B. Now on part B, it says, after the ambulance passes you. So now you're here. The ambulance has gone on ahead of you. It's here. There's your sound source. It's going 33.4. You're still going 15.6. It still has a frequency of 700. And sound is still 344 meters per second. The question afterwards says, well, what frequency do you hear now? Now that it's past you, what are you going to hear? Keep dropping erasers. So we set up our problem again. This one's actually more straightforward, much simpler algebra. We do need to decide which direction is positive and negative. So I always look at my picture. From the listener to the source is positive. If the listener's back here and the source is here, that's the positive direction. So for this part of the problem, these will both be positive numbers. We know that they're getting farther apart. This is going faster. So expect the frequency to drop. I expect to get an answer that is smaller than 700 hertz, a lower frequency sound. We hear frequency as pitch, right? When it moves away, we hear the sound drop. Okay, that's a terrible demonstration, by the way. So, frequency of the listener we'll hear now, 344. Now VL is a positive 15.6, 344. VS is a positive 33.4. Notice this is going to be a number less than 1. This bottom is bigger than this top, times 700. Let's just type it in a calculator, and that came out to be 667 hertz. So what's crucial? Formula is straightforward, but you better draw that picture and decide what direction is positive. Positive is always from the listener to the source. Okay, that concludes, that's section 12, chapter 12. We're not looking at 13 and 14 about musical instruments. So we have finished chapter 12. So I hope you have good luck with your Mastering Physics homework.